So, earlier we talked about matrices as functions, right? This is the picture I draw for functions generally, right? I have like a space over here and a space over there, and I write a function's name up here. So in this case, I'm going to write A up here. A is going to be an m by n matrix, I guess. It's got to have some size. For the purposes of not confusing the crap out of you today, should I slim this down to 2 by 2?
Well, it has to be a square.
Okay, so let's slim it to square. And then let's briefly say why we have to slim it to square anyway. So if the topic is invertible matrices, why does it have to be square?
You need to be able to take the determinant
Okay, but that's... Determinants are not covered yet for good reason. So...
Roots?
because
You know what I'm saying.
No, I have no idea what you're saying.
when you
I'll explain it later.
well, since it's a function, like, all right, when you're when you're multiplying like a thing by like a row or whatever, the dimension that you get out is like the outer dimensions. So when you're trying to, if it's like not an even amount of shit, you turn it on its side, it's like not gonna be the same thing, you know?
Okay. Yeah, kind of. Fair enough.
I don't mean like transposing it, but you know what I mean.
Yeah, so in the case of an m by n matrix, right? This thing as a function is going to take r something to r something else. You guys with me on that? Okay, so let's first figure out which one's which. So in order to take an m by n matrix and multiply by a vector x, right, so in order to apply this, what has to be true about the size of the vector x?
Has to be
Has to have like
n by
components?
something.
Okay, so
or n components, and by n.
there are two ways to walk yourself through this. The first one is confusing, and the second one is to have memorized it. So what I would recommend is that you know that when you multiply two matrices together, and I'm thinking about this vector as a something by one matrix, in order for the multiplication to work, this number here is going to have to match that number there. You guys with me on that? Really what that amounts to is the first explanation, which is that in order to do this multiplication, you're going to have to pick this vector up, turn it sideways, and drop it onto the rows. And so this vector needs to have as many entries as this matrix has columns. You guys with me on that? Because we're going to have to do that row 1 dotted with x to get that first number. And if they're not the right length, that won't make any sense. You guys all with me on that? Okay. So, once I know that the input vector has to be n by 1, this has to map Rn as a vector space. So I'm just thinking about it as n-dimensional vectors. And it's going to have to map it to R what? Where is this going to end up?
An m by 1.
Good. This is going to end up as an m by 1 vector, because that's how matrix multiplication works. So if I was writing this down, I'd be writing down this is B, B is m by 1. M. Probably should pick different letters for this, but these are the standard ones. So this vector m by 1 means that this is Rm on that side. You guys with me on that? What's going on in your head right now, Logan?
So
Is it just that noise?
No,
Echoing?
Just
No.
like the dial-up sound.
what I was thinking is, so if in our case 2 by 2 it works, you get a two-dimensional input into a two-dimensional output. But what if they're different?
Yeah, so this is the invertible part where this is going to make a difference. So this is generally a matrix as a function, right? It takes Rn, maps it into Rm. Now let me think about inverting that. So the inverse matrix is going to pull backwards, right? That's what I'm going to mean by an inverse function. And this is the same inverse function that you guys know and love for lots of stuff, right? Like the inverse function to multiply by 2 is divide by 2.
Yeah.
You guys good with that? Please notice I'm not using some examples because some examples are not actually inverse functions. So, can you guys tell me what one of the examples you know that's not actually an inverse function is? What are your go-tos for inverse functions? Yeah, that like arc, cosine, arc sine functions. Those aren't inverse functions, they're partial inverses. They have a limited domain.
Yeah.
There's some stuff there. We're not going to worry about that stuff as much here because we're going to get some cool theory out of this because everything is flat. And that's going to make passing the vertical line or the horizontal line test a little easier. So, in our case here, I have this inverse matrix. That's going to have to come back. Now let me straighten out why this case where m and n are different wouldn't work. So if you take this space over here, and you think about mapping it into that space over there, let me just assume for a second that this is the bigger one, and this is the smaller one. You guys with me on that? So if this one's the bigger one, and that one's the smaller one, in order to fit it in there, what are you going to have to do?
Smush it. Smush it.
Yeah.
Yeah, you're going to have to smush it. If you smush it, how do you unsmush it?
Stretch.
Like, you crushed some stuff. It's gone. You can't get it back because these things are flat. So the only way to smush a space with a flat function is to destroy part of it. You have to remove part of it. So, you do this all the time. If you think about taking your three-dimensional space and projecting it onto your eyeballs, right? You lose some stuff. What do you lose?
Oh.
Yeah, I mean, you lose whatever's behind the stuff that you're seeing.
Yeah.
You guys kind of with me on that? Like, you guys have lost this part of the building behind the whiteboard because it's projected in such a way that you can't pull it apart. This is actually why you have two eyes. Because having two slightly different projections lets you make some assumptions about depth. If you only have one eye, you kind of lose your depth perception. And then the only thing you can use is size cues, which makes driving with one eye really hard. What?
I mentioned drunk driving, when it starts.
Yeah, I mean, driving drunk with one eye is a terrible idea.
I mean, it's a terrible idea.
I mean, it's a terrible idea with two eyes, but yeah, it's a lot worse with one.
It helps with double vision, ironically.
Being drunk?
Yeah, like when you start seeing it, if you cover up one eye, it stops the double vision.
Oh, so you're a better drunk driver with only one eye. Is that what you're telling me?
Yeah.
By experience, yeah. Done.
No.
Okay, we're not doing this.
At all.
At any rate, the point is that if it's big to small, you've lost some stuff, you can't recover it. You guys with me on that? If you reverse this, and you do small over here, and big over here, you could think about making this kind of pass, right? Like that would work. The trouble is that this kind of pass wouldn't. And there's no distinction in this world between A and A inversus inverse. You guys see that? So if I put big over there, I have a problem, but it's with this matrix now instead of this one. So one of these matrices had to do some smashing. There's a thing called a pseudo-inverse. But to get a full inverse, I need that both wraps, so from here to there and back, results in the identity, and from here to there and back results in the identity. One of those is going to be broken in the case of these two spaces being different sizes. You guys with me on that?
Yep.
This is not a super rigorous proof. We could do a more rigorous proof by using the definition of invertible in the book. I want to give you a feel for this right now. You guys with me on the feel of this? Okay. So, our matrices, if they're to be invertible, have to be square. So that's going to result in my A n by n. So that means this space is Rn as a vector space, and this space is also Rn as a vector space. You guys with me on that? Okay. So this is not enough necessarily to say that A inverse exists. So just being square isn't enough. You guys give me an example of a matrix.
With a row of zeros. Can't do it.
Yeah, let's beef that example up to the kind of maximally isn't going to work. So I want an example of a matrix that's not invertible.
Yeah.
And I suppose since I'm talking about invertibility, this is a not example. This is like the most not example you can get.
Would nothing but ones also fall into that?
Yeah. So let's see if we can figure out some kind of criteria, right? So for right now, I just want to dwell on this thing for a hot second, and then we'll get a criteria. So what's this thing's name?
The zero vector. The zero matrix.
Good. Yeah, the zero vector, right, would be a vector with all zeros in it. This is not a vector, it's a matrix, so its name is the zero matrix. This thing is kind of common enough that we'll end up writing 0, 2 by 2. You guys with me on that?
Yes.
So this is sort of the least invertible a matrix can get. What is the sort of most invertible a matrix can get?
The identity.
I don't
The
know.
identity matrix.
Yeah, the identity matrix is kind of the most invertible a matrix can get. Why?
Because there's a solution.
I
Like,
think it's just the inverse is like itself.
Yeah,
there's a count.
Yeah.
Yeah, the action of this thing, mapping R2 to R2, is it doesn't do anything, right? So how do you undo not doing anything? You don't do anything. So this thing has the property that the 2 by 2 identity matrix's inverse is the 2 by 2 identity. You guys with me on the Y there?
Yeah.
Yeah. Okay, so that's an option. What's a not that option that's invertible?
Not that option.
Anything with independent columns.
Like,
Yeah, so there's this thing in the book about independent, dependent columns we'll get to in like 2 minutes. But I want one more example right here.
1, 2, 3, 4.
See, that's true, right? So 1, 2, 3, 4 happens to be invertible,
Yeah.
but why is it invertible? Like, can you see it right off the bat? Yeah, so you can use the definition that the rows need to be independent or the columns need to be independent, and notice that this satisfies that definition. You guys with me on that? But we needed a little more tool, right? I think there's another matrix like the identity matrix that we can see right off the bat is invertible without thinking about independence of columns and rows.
Just the reflection of that. Okay.
So what does this matrix do?
It's gonna see itself.
It transposes stuff.
Yeah, if I think about the action of this matrix, right, this is taking this guy, I'm going to multiply this by a two-dimensional vector xy. If I do that multiplication, what do you get?
You get yx.
Okay. Okay, so what did it do? Like, as an action, it flips the coordinates, right?
Yeah.
This is the reflection matrix. So it swapped the coordinates. So if I want this thing back, like if I want to reverse this action,
Just multiply by again.
the same metrics again.
yeah, I just need to reverse them, right?
Yeah.
So the inverse of this matrix is again itself. You guys with me on that?
What's that one
Yeah.
called?
I call this one the reflection matrix. It reflects along the across the line y equals x. In the book, you'll find several other matrices with this property that are their own inverses. There are a few of them. They're kind of convenient. You know some functions like this. The identity function is one, right? F of x equals x. Another one is f of x equals 1 over x. Does anybody know the other one?
X squared?
No.
No?
That doesn't have an inverse. It has a partial inverse.
Yeah, okay. Fair point.
What'd you say? F of x is equal to
So-
1 over x?
There are 3 examples, well, 4 examples of this in the F mapping R to R. There are 4 easy examples.
Yeah.
Those are f of x is x, f of x is 1 over x,
X.
f of x is,
E to the X?
say that again?
E to the X? Negative 1 over X?
And then the 4th one is f of x is negative 1 over x. So these are kind of the reflections that one-dimensional functions can have. Should be noted, these two are not matrices, nor are they expressible as such. This is a fundamentally nonlinear transformation, so these are not something we'll talk about in this class. This is the matrix 1.
Nice.
Right? Mapping R1 as a vector space to R1 as a vector space. That is the 1 by 1 identity matrix. How about this one?
Negative 1?
Yeah, that's the matrix negative 1. 1 by 1, mapping R1 to R1. So I bet that gives you an option that you could do. You could probably make one more of these really easily now.
Make them negatives?
Yeah, negative the identity matrix is its own inverse. Negative this thing is its own inverse. You can even put a negative on one or the other of these, and they'll still be their own inverse. Is that kind of making some sense?
Yes.
That probably isn't true for this one. Yeah, that's not true for this one. So, at any rate, these are kind of my go-to examples for invertible. This is my go-to non-invertible one. Usually I appoint somebody to be the keeper of the 0 vector and the 0 matrix. Anybody want that job?
What does it entail?
It entails every time I say something, you think about whether it's true for the 0 vector and the 0 matrix. And then if it's not, bug me. Cool. Ian, you're in.
Oh, dang.
Alright.
Nice.
Don't let me down, buddy.
I will.
If Alexis was here, she'd be it. I think Alexis actually was it last time. So, let's have our kind of secondary criteria. So the book makes this claim that a matrix is invertible if and only if the columns are linearly independent. They also say the same statement for rows. Be good with those? So, in order to use this, I probably need to know what the word linearly independent means. You guys cover that? Have you seen that?
Yeah, but like,
I've
I
seen
was gonna
it
ask
before.
way more clarification.
Okay, we need some clarification on
Yeah.
linearly independent. Okay, cool. So, in order to use this, let's go get linear independence. This video is getting a little long, so let me stop this here and say there is this criteria. This is not just a claim, this is true. Okay? You could take this as the definition of invertible, although I tend to not.